Okay, so this is the 2022 paper, question 1A. So ask you to draw a Lewis structure for BrO3 minus and SO32 minus. So for the first step of this kind of question, you first have to identify like how many electrons you guys have. So for Br you have 7, then for each oxygen you have 6. Since you have 3 oxygen, it'll be 6 times 3, and you plus the additional uh, electrons from the ion. Yeah. So total you have 26 electrons, and you can divide by 2 to make it easier, which is 13 groups. Then after that, you identify your central atom, which is the Br, and you connect it through single bonds to your peripheral atoms, which is your oxygen. After that, you fill up the octets of your peripheral oxygen before filling up the Br one. So then you realize that, oh, actually oxygen can form double bonds. So you form double bonds with the Br, then you get the resonance structures. Yeah. So in this case, there will be a total of 4 resonance structures. Okay, so after you've drawn your resonance structures, the next will be to identify which is the most possible one. You do that through formal charges. So to calculate formal charge is basically your valence electrons minus your lone pair electrons minus half of your bonding electrons. So for oxygen, you have 6 valence electrons, you minus 6 lone pair electrons, and you minus half of the bonding pair, which is 1, which you get a net of minus 1. So by doing that, you would be able to see that actually the third structure is the most possible one, because the negative charge will be on the more electronegative atom, which is the -1, and also like overall he has the least amount of formal charges, which is what a structure would want to like head towards lah. So I would draw the structure again below just to make it clear for the oxidation number. Yeah. So for oxidation number, right, uh, basically you need to memorize that oxygen is -2 in everything except when it's bonded to fluorine or it's in a peroxide. So even in this case that it was double bond or single bond, it will still have oxidation number of -2. So your oxidation number would your overall oxidation number of the molecule would equal to the charge of the molecule. So it'll be -2 times 3, which will be -6, and then you're supposed to add a number so that you get -1 total. So that's why your oxidative number of Br is +5. Okay, so to the next molecule, SO3 2-. Well, actually the amount of electrons, like the total electrons would be actually the same as the BrO3-. So that like interesting lah. I don't know. I don't know if it's interesting or not. But anyways, it will be 13 groups. Then you do the same thing. First you identify the central atom, which is S, and then you connect it to your peripheral atoms by a single bond. You fill up the octet of the peripheral atoms first before your central atom. Then after that, you can see that actually oxygen can form double bonds. So you create the double bonds, and there'll be again 4 resonance structures. Okay, so after you have drawn finish all your resonance structures, next will be the formal charge. So from what we got from the BrO3 earlier, we will know the formal charge of single bonded single bonded oxygen and double bonded oxygen. So yeah, the single one will be -1 and O. So you don't have to calculate it again now because it's basically the same thing. But you do have to calculate the sulfur since the sulfur is different from the Br. Yeah. So yeah, this is how you calculate the formal charge of the sulfur, which is yes 6 valence electrons minus your 2 lone pair electrons and then minus the 3 from the bonding pairs. Okay, so after you've drawn your resonance structure, now is to find the most possible one, which is number 2, because the negative charge is on the more electronegative atom. Right, so now for the oxidation number, we already know that oxygen has a oxidative number of -2. So the charge of your overall charge of the molecule must equal to the sum of the oxidation numbers. So the -2 will equal to sulfur plus -6. So your sulfur will equals to 4. Yeah. Okay, so on to part B, where we're asked to find the ideal bond angles for carbon, nitrogen, and oxygen in the three molecules. So I named it 1, 2, and 3, so it's easier for you to see. And there's something else that you need to know is that lone pair repulsion is the strongest, followed by lone pair, and bond pair. Yeah. So in molecule 1, you can see that the carbon is bonded to two hydrogens by one single bond and to a nitrogen by a double bond. So ideally it would be a 120 like trigonal planar structure, but because of your double bond, it has greater electron density that will push the other two bonds closer to each other. So your actual will be 120 degrees, less than 120 degrees. And for your nitrogen, like you can see there's the lone pair there. So yeah, you know that there's lone pair repulsion, which will lead to a less than 120 degrees. And also there's a double bond there. So for oxygen, it's like the same as water lah. So your ideal would be 109.5 degrees because there's two lone pair electrons and two bond pairs. But now it will be less than 109.5. Yeah, next to number 2 will be the carbon. So there's 4 bonds. So no lone pairs, so it will be exactly the same as the ideal, which is 109.5. And for the oxygen, because of the two lone pairs, it will again be less than 109.5. Now on to molecule 3, there's actually 3 different oxygens here, A, B, and C. So for A, you actually have 2 lone pairs and 1 double bond, which will create, ideally it's 120, but it will be less than 120 because of lone pair and also the double bond. And for the nitrogen, I mean for the oxygen B, right, you have 3 lone pair electrons. So that means that will again create less than 109.5, and that's the same for oxygen C. And for the nitrogen, you have 1 double bond and 2 normal bond. So that means ideal will be 120, but actually will be less than 120 because of the double bond. Okay, so part C, we're asked to identify which has the net dipole moment. So we'll definitely have to draw the Lewis structure because the question already asked for it, and we also need to identify which has the dipole. So dipole movement is caused by first having polar bonds, and secondly, uh, a non-symmetrical shape of your molecule, which your phosphorus, Br, and sulfur has. On the other hand, the boron and the last sulfur is symmetrical. That's why the net dipole movement cancels out. That's why there's no net dipole. I mean, the dipole movement cancels out. That's why there's no net dipole movement. Yeah. Okay, question 2 part A is question about hybridization. So you first have to know what electron group is. So what is an electron group? It can be a single bond, a double bond, or a triple bond, or also can be a lone pair electrons. All these count as only one electron group. So even if you have a double bond, it's still counted as one. Yeah. So taking a look at the first carbon on the most left side, you would see that it's bonded to 3 hydrogen and 1 sulfur. So you have total of 4 bonds. So it will be sp3 because S is 1, P there's 3 P, so total is 4. Using that, you can use it to calculate the rest lah. I don't think you need much help with that anymore. Should be quite easy question for you guys. Okay, on to question 2, part B. Okay, I don't like this question because it's very time consuming. But it's basically the same thing as in question 1. You first have to draw the structure. Uh, there will be resonance structures for the first 3. So you have to find the most stable one. And then from there, you find the hybridization. So maybe you guys have an easier way to do it, but this is how I did it. So first I draw the structure, then see how many electrons groups each has. Okay, so question 2 part C is on MO diagrams, which is another very time consuming question. So first you need to know which homonuclear molecules would mix. So BCN will mix, like boron, like B2, C2, and N2 will mix. But your O2, F2, and your Ne2 will not mix because of the difference in the P and S, right? Yeah. So anyways, after you identified that this is O2s, it will have no mixing. So your sigma would be below in energy level than your pi. Okay, the next would be to draw the diagram. Yeah. Okay, so I've gone ahead and drawn the diagram to not waste time lah. But anyways, yeah. So your HOMO, you can see that it will be the pi star. I mean the pi antibonding, and then your LUMO would be the sigma antibonding. And because you have your SUMO like singly unoccupied molecular orbital in your pi antibonding, you would have a paramagnetic molecule. Yeah. So I'm not going to draw it for the rest of the other molecules. I'll just skip forward. Okay, skipping forward, let's say you join all of it. Now you have to identify the bond order. So the bond order will be the amount of electrons inside your bonding orbitals minus your antibonding orbitals divided by 2. So in your O2 will be 6 in the bonding, which is the 6 below, minus the 2 on top, then divide by 2, which will be 2. So you guys need to know that higher bond order means that it's a stronger bond. That means your bond length will be decreased. So it's kind of like inverse relations. So the ones that actually have the lowest bond order would have the highest bond length, which is what you can see here lah. Okay, on to NMR. So I'm going to skip most of it because I think it's quite easy. So only question B, I think some people would have questions. So B actually couples to 6 hydrogens. I mean, it couples to two of the A's. And since these 6 hydrogens are magnetically equivalent, so it'll be 6 plus 1. So it'll actually split into 7 signals. That's why it's a septet. Yeah. So then on to the second part of the question, it asks to predict the range of the coupling constant you expect for the most dishielded signal. But actually the most dishielded signal would be the one bonded to the oxygen. And if you're bonded to oxygen, that means that you can't couple. So the coupling constant is actually 0. Yeah, I think that's what the question is asking. I'm not sure. Okay, so for question 3A is on chemical kinetics. So they ask us to find the reaction order for A, B, and C. So to find direction order of A, we first have to find 2 experiments that changes A but keeps B and C the same, which is experiment 2 and 3. And for this, there's actually a formula. And you can memorize it if you want, but I think most people don't memorize it. They just use the math instead because it's more intuitive. Okay, so first is the ratio of concentration to power x equals to the ratio of initial rates. So the ratio of concentration is 3.22 times 10 to the power negative 4 over 1.4 times 10 to the power negative 4. And that to the power x will be equal to the ratio of your 8.37 times 10 to the power negative 6 over 2.4 times 10 to the power negative 6. Yeah, so you're supposed to find x that will give you that value. And by calculating your x will actually equals to 1.5. Like, if you don't know how to do this, you just have to ln both sides to bring down the x. Yeah, so I think it's pretty easy from there on. Okay, so after you get x equals to 1.5, you can write out like the rate law for it. I mean, like you know A lah, so it's 1.5, then B will be to another coefficient, and then C will be to another coefficient. Or what am I writing? Okay, anyways. Yeah. Okay, so I'm just gonna skip forward since it's the same method for everything. And yeah, your reaction order for A will be 1.5, for B is -2, and C is -0.5. So for part B of this question, it will be to find the rate constant, which you know that your rate will equals to rate constant times your concentration to the power of your reaction order. Yeah. So just submit the values actually. It's quite simple. You can pick any of the experiments to do it. So I just pick the first one because it's the first, yeah. Okay, so your answer will be k equals to 2.3 times 10 to the power -8. Okay, so part B of this question, it will ask you to determine the amount of whatever that compound is after 61 hours. So you first have to identify that this reaction is actually first order. So you do that by seeing that the units. So the units of your rate constant is per second. So per second will indicate that it's first order. So then the first order integrated rate law would be the ln one lah. So basically just submit the values. You already know everything, the rate constant, you already know your time. Actually, the time need to convert lah because you have to convert to seconds from hours. And the conversion is pretty simple. I written there already. And after everything, your your final concentration would be 0.02507. Yeah. Okay, so for the second part of this question, we are asked to find the activation energy. So you see there's temperature, there's activation energy. So you need to know that this is a Arrhenius equation. And the second thing you need to know is that we cannot use degrees Celsius, we need to use Kelvin. So you have to plus 273.15 to 25 degrees Celsius and 55. So this is the Arrhenius equation here. Yeah, you need to memorize this lah. Then basically just same thing, sub it in and isolate the EA to get the EA. So in the answer they send in the chat, the EA is negative, and that's not correct lah. It's actually supposed to be positive, yeah. So it's 151,000, and this is in joules. So to convert the kilojoules, you have to divide by 1,000. Yeah, so it's 151. And you can check that this is actually correct because by increasing temperature, your rate increases. So it cannot be negative activation energy. Yeah. Okay, so part C of this question will be asking for the half-life. So you should know that the half-life of first order would be a ln 2 over k. So you can isolate k to get the value of k lah. Yeah. Then you need to know the first order integrated rate law also, so that you can find the concentration of k after how many seconds. So this is the integrated rate law lah. Then basically you just start in values to find the concentration of a after 4.2 whatever seconds that is. Yeah, and also like keep in mind that you need to convert that whatever seconds into normal seconds. I'm not sure if it's in the chemistry data booklet. I have no idea. I haven't looked at it, but yeah. So anyways, the 4.2 whatever seconds would be equal to roughly like 4.2 times 10 to the power of -6. Then after that, just stop everything in because the units is correct now. Okay, so once you submit the values, you'll get ln of AT equals to 2.0115. And if you E both sides, you get 7.474. So this is the current pressure of the reactant. So you take your initial value minus your current value, you get how much pressure has been, like pressure or concentration has been reacted. So since the reactant to product ratio is 1:2, so you have to multiply that by 2 to get the pressure of product that has been formed, which is 5.052. Okay, so last question, question 4. I'm not going to do the rest because it has entropy and Gibbs free energy, which we are not taught about. So yeah. So this question is a thermodynamics question. So first thing you need to know that your delta E is actually delta U. Yeah, some textbook write it differently, but it's exactly the same thing. Okay, so the next thing you have to realize is that the enthalpy or your standard enthalpy is actually -1256. And this is proportional to the amount of moles that reacted. And in this case, we have 18 grams that's reacted. So you have to find the moles of 18 grams. So 18 over your molar mass, which is 26, would give you 9/13. So by multiplying the moles with your reaction, I mean your enthalpy, you'll get your actual enthalpy of the reaction. Makes sense, right? Yeah. And that'll be -11 something. Oh yeah, 11304/13. Yeah. So after this, you will need to know your equation for enthalpy, which will be the change in enthalpy will equal to the change in internal energy plus your pressure times change in volume. Okay, so after you get this equation, you can sub in the enthalpy and your internal energy change to get this new equation. And from there, you have to realize that your pressure is in atmosphere, but your enthalpy and your energy change is in kilojoules. So you have to convert kilojoules to joules, then convert it back to liter per atmosphere. And 1 liter per atmosphere, or whatever that shit is 101.3 joules. So to convert from kilojoules to joules, you times 1000 lah. Then after that, you times 1000, then you divide by 101.3, yeah, to get your liter per atmosphere. So by rearranging the equation, you would get -11304 divided by 13 plus 863 equals to your change in volume. and you divide the left side by 0.1013, I think. Yeah. So you divide it by that to get it in liters per atmosphere, and you realize that your change in volume would equal to negative 64 something something something. Yeah. And your change in volume will actually be your final volume minus your initial volume. Your final volume is what you want to find, and your initial volume is 80. So final volume minus 80 will equal to negative 64. You bring the 80 to the other side, you get final volume is 15.4544 liters. Yeah.